By the closing years of the 19th century, physics stood with an air of triumph that bordered on arrogance. For more than 2 centuries, the laws of motion laid down by Isaac Newton had described the movements of falling apples, orbiting planets, and crashing waves with astonishing precision. James Clerk Maxwell had woven electricity, magnetism, and light into a single elegant framework of equations, revealing that light itself was an electromagnetic wave rippling through space. Thermodynamics had mapped the rules of heat, energy, and work, giving engineers the power to build engines that drove the industrial age. To many scientists, nature seemed almost fully decoded, its secrets reduced to predictable laws and tidy mathematics. The universe appeared to be a vast machine, intricate but ultimately understandable, governed by continuity, determinism, and smooth change. In this world, every physical quantity varied in a continuous manner. Energy could take any value. Motion could be divided into ever smaller pieces without limit. If one knew the position and velocity of every particle at a given moment, the future could, in principle, be calculated exactly. This belief in determinism was not merely philosophical. It was a practical conviction supported by countless successful predictions. Planetary orbits, the paths of projectiles, the behavior of gases, and the propagation of light all seemed to obey clear, unbroken rules. Many physicists genuinely believed that their task was nearly finished, that only minor adjustments remained before a complete description of nature would be achieved. Yet beneath this confidence, subtle tensions were building. Certain experiments, at first treated as technical annoyances, began to resist explanation. The cracks were small, almost invisible against the vast structure of classical theory, but they were deep. The more precisely scientists measured natural phenomena, the more these inconsistencies stood out. Reality, it seemed, was not as obedient as the equations suggested. One source of trouble came from the study of heat and radiation. According to classical ideas, matter consisted of tiny particles in constant motion, and temperature was a measure of the average kinetic energy of these particles. Light, on the other hand, was understood as a wave, an oscillation of electric and magnetic fields traveling through space. These pictures worked well separately, but when combined, they created puzzles. Heated objects emitted radiation in patterns that did not align with predictions based on classical electromagnetic theory and the principles of energy distribution derived from thermodynamics. Another growing problem involved the structure of matter itself. Atoms were accepted as real entities, but their internal workings were mysterious. Experiments with gases showed that atoms emitted and absorbed light at very specific frequencies, producing sharp spectral lines rather than a continuous range of colors. Classical physics offered no clear reason why atoms should favor particular frequencies. If electrons were imagined as tiny charged particles orbiting a nucleus, Maxwell's equations implied they should radiate energy continuously, spiraling inward and collapsing into the nucleus in a fraction of a second, yet atoms were stable, matter did not self-destruct. This stability stood in silent defiance of classical expectations. The behavior of electrons in metals introduced further confusion. As electrical conduction was explored, scientists observed patterns that did not fit neatly into the classical picture of particles bouncing around like miniature billiard balls. Measurements of specific heat, capacities of solids also refused to cooperate. Classical theory predicted that each degree of freedom in a system should contribute equally to its energy, a result known as the equipartition theorem. But experiments at low temperatures showed that solids stored less heat than expected. Some forms of motion seemed to freeze out, as if nature imposed restrictions that classical physics did not recognize. Light itself became a source of unease. Interference and diffraction experiments had strongly supported the wave theory of light, yet other observations hinted at a more complex story. When light shone on certain metals, electrons were ejected, but the details of this effect did not match classical wave predictions. The energy of the ejected electrons depended on the frequency of the light, not its intensity, an odd result that lacked explanation within existing frameworks. These anomalies did not immediately overthrow classical physics. Instead, they accumulated slowly, like unanswered questions in a courtroom. Each one could be set aside, treated as a special case, or blamed on experimental limitations. But as techniques improved and data grew more precise, the list of exceptions expanded. The sense of near completion began to fade, replaced by a quiet unease. The old theories were still powerful, but they were no longer universally reliable. At the heart of the crisis was the assumption of continuity. Classical physics treated energy as infinitely divisible, capable of flowing smoothly between systems in any amount. Waves could have any amplitude, particles any energy, but the stubborn experimental facts suggested that, at microscopic scales, this smoothness might break down. Certain energies seemed preferred. Certain interactions occurred in discrete steps. The idea was unsettling because it threatened the very foundations of the mechanical worldview. The philosophical implications were just as troubling as the technical ones. Determinism had been a guiding principle. Given complete knowledge of the present, the future was fixed. But if the underlying processes of nature involved sudden jumps or restrictions not captured by continuous equations, predictability itself might be limited. The notion that nature could be fundamentally discontinuous or probabilistic clashed with centuries of scientific intuition. The crisis was not a dramatic collapse, but a gradual erosion of certainty. Senior physicists often clung to the belief that classical ideas would ultimately prevail, that the anomalies would be resolved with clever refinements. Younger researchers, however, sensed that something deeper was wrong. The old framework, magnificent as it was, might not be the final word. The situation resembled a map that had guided explorers successfully across vast territories, only to fail in a newly discovered landscape. The principles of Newton, Maxwell, and classical thermodynamics remained valid in the macroscopic world of everyday experience. Bridges still stood, planets still followed predicted paths, and engines still ran. But when scientists peered into the realm of atoms and radiation, the map's edges frayed. New terrain demanded new concepts. What made this period so pivotal was not just the presence of unsolved problems, but the nature of those problems. They pointed toward a limitation of the core assumptions about how energy, matter, and light behaved. The difficulties were interconnected, appearing in radiation, atomic structure, heat capacities, and electron behavior. It was as if multiple threads all led to the same hidden knot. The crisis in classical physics was therefore a turning point in the history of science. It showed that even the most successful theories have domains of validity. Beyond those domains, new principles may govern. The confidence of the 19th century gave way to the uncertainty of the 20th, setting the stage for a conceptual revolution. The stage was prepared not by bold speculation at first, but by careful measurement, stubborn data, and the refusal of nature to conform to established expectations. Out of this tension would emerge a new constant, a new way of thinking, and an entirely different picture of reality. But before those ideas took shape, the old order had to confront its limits. The crisis was the necessary prelude, the moment when the familiar world of smooth curves and deterministic motion began to dissolve, revealing that beneath the surface, nature followed rules more subtle and surprising than anyone had imagined. In laboratories lit by the soft glow of heated metal and the faint shimmer of experimental apparatus, physicists at the end of the 19th century turned their attention to a deceptively simple question: how does a hot object glow? It was not merely curiosity about color or brightness. They wanted a complete mathematical description of how energy is emitted as radiation by matter in thermal equilibrium. The problem seemed technical, almost routine, especially compared with the grand achievements of celestial mechanics and electromagnetism. Yet this humble question would become one of the greatest crises in the history of science. To study thermal radiation in a clean, idealized way, physicists imagined a perfect absorber and emitter of radiation, an object that would take in all incoming light and re-emit energy in a way that depended only on its temperature. This ideal object was called a blackbody. In practice, a small hole in the wall of a heated cavity served as an excellent approximation. Radiation entering the hole would bounce around inside, getting absorbed and re-emitted so many times that it reached equilibrium. The radiation coming out of the hole no longer carried information about the material of the walls, only about temperature. This made it a universal system, a kind of reference source for studying the laws of radiation. When scientists measured the spectrum of this radiation, they found a distinct pattern. At low frequencies, the intensity was small, then it rose to a peak at a frequency that increased with temperature, and finally it fell off at higher frequencies. The curve had a smooth, well-defined shape, shifting toward higher frequencies as the object grew hotter. Experiments became increasingly precise, and the data were reliable. The challenge was theoretical, to derive this curve from the known laws of physics. Classical physics offered the tools. Electromagnetic waves could exist inside the cavity in many possible modes, each corresponding to a standing wave pattern. Thermodynamics and statistical mechanics provided rules for how energy should be distributed among these modes. According to the equipartition theorem, each degree of freedom in thermal equilibrium should carry, on average, the same amount of energy, proportional to temperature. This principle had worked beautifully for gases and many mechanical systems. Applying it to electromagnetic waves seemed natural. The calculation proceeded step by step. First, count the number of possible wave modes in the cavity for each frequency range. This number increased rapidly with frequency. Higher frequencies meant shorter wavelengths and more ways to fit standing waves inside the cavity. Then, assign to each mode an average energy based on the equipartition theorem. Multiply the number of modes by the energy per mode, and you obtain the predicted energy density of radiation as a function of frequency. At low frequencies, the result matched experiments reasonably well. The curve rose with frequency, just as observed. But as the frequency increased, something alarming happened. The number of modes grew so quickly that the predicted energy density did not peak and fall. Instead, it kept rising without bound. In the ultraviolet region and beyond, the equations said the energy should approach infinity. A warm object, by this reasoning, would radiate an unlimited amount of energy at high frequencies. This was not a small discrepancy, it was a catastrophic failure. The prediction was not merely wrong in detail, but absurd in principle. This divergence became known as the ultraviolet catastrophe. The name captured both the spectral region, where the problem was most dramatic, and the sense of theoretical disaster. Classical physics, so successful elsewhere, had produced an infinite result for a clearly finite physical quantity. No real object radiated infinite energy. The glow of heated metal did not suddenly explode into an overwhelming ultraviolet blaze. The laboratory measurements were clear, and they contradicted the theory decisively. The catastrophe struck at the heart of several pillars of classical thought. Maxwell's electromagnetic theory was not in doubt by itself. It had passed numerous tests. Statistical mechanics, with its probabilistic treatment of large numbers of particles, was also well established. The equipartition theorem followed logically from the assumptions about how energy distributes among degrees of freedom. Yet, when these solid pieces were combined, they led to nonsense. It was as if well-crafted parts of a machine, assembled together, suddenly refused to function. Physicists tried various adjustments. Perhaps the walls of the cavity did not behave ideally. Perhaps matter and radiation did not interact as simply as assumed. Maybe unknown mechanisms limited high-frequency oscillations, but each attempted fix felt ad hoc, lacking a clear theoretical foundation. The problem was stubborn because it did not stem from a small miscalculation. It came directly from the fundamental assumption that energy could be shared continuously and equally among all possible modes. The deeper issue was the infinite divisibility of energy in classical theory. If each electromagnetic mode, no matter how high its frequency, could possess any amount of energy and was entitled to its share, then the enormous number of high-frequency modes would dominate total energy. Nature, however, behaved differently. Experiments showed that high-frequency radiation was suppressed. The intensity dropped sharply instead of diverging. Something prevented energy from flowing freely into those modes. The Blackbody problem became a focal point for theoretical efforts because it was both fundamental and precise. Unlike the messy complexities of chemistry or biology, it involved pure radiation in a controlled environment. The discrepancy between theory and experiment could not be blamed on unknown materials or complicated structures. It pointed directly to a flaw in the basic principles. Emotionally, the situation was unsettling. Many physicists had grown up in a tradition that celebrated continuity and determinism. The idea that energy might not distribute smoothly, that certain frequencies might be restricted, felt almost heretical. Yet the data would not go away. The ultraviolet catastrophe was a clear sign that classical physics, though powerful, had limits. This crisis was also a lesson in the power of idealization. The Blackbody was a theoretical construct, but it captured essential features of real systems. Because it stripped away material details, any failure of theory in this context indicated a deep problem, not a superficial one. The simplicity of the model made the contradiction sharper, not easier to dismiss. As the 19th century closed, the Blackbody radiation problem stood like a warning signal. It showed that the classical picture of waves, energy, and equilibrium could not be universally valid. The catastrophe was not just about ultraviolet light. It was about the structure of physical law. Something fundamental about how energy and matter interacted was missing. The stage was set for a radical shift. A solution would require abandoning or modifying cherished assumptions, especially the belief in continuous energy exchange. The path forward was unclear, and no one yet spoke of quantum theory in its modern sense. But the ultraviolet catastrophe had already done its work. It had exposed a crack in the classical edifice wide enough for a new idea to enter, an idea that would change physics forever. Max Planck did not see himself as a revolutionary. He was known among his colleagues as cautious, disciplined, and deeply respectful of established principles. His career had been built on thermodynamics, a field grounded in careful reasoning and general laws. He believed in order, in the reliability of physical theory, and in the continuity of nature. Yet the problem of thermal radiation, stubborn and embarrassing, drew him into territory where those beliefs would be tested. The measurements of blackbody radiation were clear. The spectrum had a definite shape that shifted with temperature, and no classical formula could reproduce it across all frequencies. Some equations worked at low frequencies, others at high ones, but none captured the full curve. Planck was determined to find a single expression that matched the data exactly. At first, his approach was pragmatic. He searched for a mathematical interpolation, an equation that fit the experimental points, without necessarily worrying about deep physical meaning. He imagined the walls of the blackbody cavity not as continuous matter, but as containing tiny electric oscillators. These oscillators, microscopic charges bound in atoms, could vibrate and exchange energy with the electromagnetic field inside the cavity. Radiation would be emitted and absorbed through these oscillations. This picture was still classical in spirit. Oscillators were familiar objects, and electromagnetic waves were well understood. The difficulty lay in describing how these oscillators shared energy. Classical statistical mechanics said energy could vary continuously and be distributed smoothly. But when Planck tried to use these ideas, he ran into the same divergence that had plagued others. The energy at high frequencies grew without limit. The data demanded a different distribution, one that suppressed high frequency contributions. In an act of intellectual desperation, Planck made a bold move. To derive the entropy of the oscillators, he adopted a combinatorial method inspired by Ludwig Boltzmann, who had linked entropy to the number of microscopic arrangements consistent with a macroscopic state. Planck divided the total energy of the oscillators into a number of equal, finite elements. Instead of allowing energy to vary continuously, he treated it as composed of discrete pieces, each of a certain size proportional to the frequency of the oscillator. This step was subtle but profound. He assumed that an oscillator of frequency nu could only exchange energy in multiples of a basic unit, epsilon equals h nu, where h was a nu constant. The total energy could be 0, h nu, 2h nu, 3h nu, and so on, but not intermediate values. Planck did not claim that energy was truly discontinuous in nature. He viewed the discretization as a formal device, a mathematical trick to make the counting of states manageable. Yet, when he carried out the calculation, the result was astonishing. The formula he derived matched the experimental blackbody spectrum perfectly. The constant h entered quietly, as a parameter needed to fit the curve. Its value was extremely small, far below anything noticeable in everyday phenomena. Because of this, the consequences of discretization had gone unnoticed in the macroscopic world. Only in the microscopic interactions between radiation and matter did the granularity matter. The formula Planck presented in 1900 described the energy density of blackbody radiation as a function of frequency and temperature with remarkable accuracy. At first, Planck himself hesitated to interpret the result literally. He was uncomfortable with the idea that energy might not be continuous. For him, the quantization was a feature of the oscillator's interaction with radiation, not necessarily a universal principle. He hoped that a deeper classical explanation would eventually be found, but the mathematical structure of his derivation pointed elsewhere. The success of the formula depended fundamentally on the assumption that energy exchange occurred in discrete units. This assumption broke with a long tradition in physics. Continuity had been a guiding principle, from the smooth trajectories of mechanics to the unbroken fields of electromagnetism. Introducing indivisible energy elements suggested that nature at its core might be granular. The oscillators could not emit a fraction of a quantum. They had to jump from one energy level to another. The change was not gradual but stepwise. The concept of quantization also introduced a new relationship between energy and frequency. The unit of energy was proportional to frequency, meaning higher. Frequency oscillators had larger energy steps. This explained why high frequency radiation was suppressed at ordinary temperatures. To excite those modes required larger energy quanta, which were less likely to be available. The ultraviolet catastrophe disappeared because energy could not be partitioned arbitrarily among infinitely many high-frequency modes. Planck's presentation of his work to the German Physical Society was modest. He emphasized the agreement with experiment and the formal derivation without declaring a revolution. Yet the constant he introduced would become one of the most fundamental numbers in physics. It set the scale at which classical ideas fail and quantum effects dominate. Wherever H appears, the discreteness of nature reveals itself. The deeper meaning of Planck's assumption unfolded gradually. Other physicists began to explore its implications, sometimes taking it more seriously than Planck himself. The idea that energy exchange was quantized opened new ways of understanding atomic spectra, specific heats, and the interaction of light with matter. What began as a mathematical convenience turned into a principle about the structure of reality. The boldness of Planck's step lay not in dramatic rhetoric, but in quiet necessity. Faced with data that defied classical reasoning, he allowed himself to modify a foundational assumption. He did not abandon rationality, he extended it into new territory. The quantization of energy was not proposed as philosophy, but as the simplest way to make theory and experiment agree. In retrospect, this moment marks the birth of quantum theory. The constant H became the hallmark of the new physics, appearing in equations that describe atoms, molecules, and subatomic particles. Planck's oscillators were the first systems to be treated with quantized energy levels, a concept that would soon apply to electrons, photons, and beyond. What makes this story compelling is the contrast between intention and outcome. Planck sought to preserve classical order, yet his solution undermined its core. By introducing discrete energy elements, he opened the door to a view of nature that is probabilistic, discontinuous, and deeply counterintuitive. The old picture of smooth change gave way to one of jumps and quanta. The assumption of energy quantization, born from the Blackbody problem, was the turning point. It showed that the crisis in classical physics could not be resolved by minor adjustments. A new constant, a new rule, and a new way of thinking were required. Planck's hesitant step became the foundation of an entire century of physics, revealing that at the smallest scales, the universe does not flow like a continuous river, but advances in tiny, indivisible steps. When Max Planck introduced his new constant at the dawn of the 20th century, he could not have known that this small number would become one of the central pillars of modern physics. At first glance, it seemed like a mere fitting parameter, a quantity inserted into an equation to make theory match experiment. Yet its presence signaled a profound shift in how energy, matter, and motion were understood. This constant, later denoted by the symbol h, carried within it the scale of the quantum world, marking the boundary where classical intuition gives way to a deeper, stranger order. The constant appeared in a simple but revolutionary relation. The energy associated with a mode of frequency nu is given by E equals h nu. In classical physics, energy had no such restriction. A system could, in principle, possess any energy value, changing smoothly as conditions varied. But this equation implied that energy exchange occurs in steps proportional to frequency. The higher the frequency, the larger the energy unit. This was not a small correction, but a fundamental rule. Energy was no longer infinitely divisible. It came in packets whose size was set by h. The numerical value of Planck's constant is extraordinarily small, about 626 times 10 3 joule-seconds. This tiny magnitude explains why quantum effects are not obvious in everyday life. For large objects with large energies, the discrete steps are so minuscule relative to total energy that motion appears continuous. A moving car does not reveal its quantum nature because the difference between adjacent energy levels is unimaginably small. But for atoms, electrons, and photons, where energies are correspondingly tiny, the granularity becomes decisive. The units of h are also revealing. A joule, second, combines energy and time, linking two quantities that classical physics treated as distinct. Later developments would show that h connects energy with frequency, momentum with wavelength, and action with phase. It became clear that this constant was not tied to a single phenomenon, but woven throughout the structure of physical law. One way to grasp its meaning is through the concept of action, a quantity used in classical mechanics defined as energy multiplied by time or momentum multiplied by distance. Classical systems often involve actions much larger than h, which is why classical equations work so well at macroscopic scales. But when the action of a system approaches the order of Planck's constant, quantum behavior dominates. The constant thus sets the scale at which the classical description breaks down. In atomic physics, h determines the allowed energy levels of electrons bound in atoms. Electrons cannot orbit the nucleus with arbitrary energies. Only specific discrete values are permitted. These levels arise naturally when wave-like properties of matter are considered, with boundary conditions that depend on Planck's constant. The stability of atoms, the existence of chemical elements, and the structure of the periodic table all trace back to this quantization. Without h, electrons would spiral into nuclei or drift away, and the rich variety of matter would not exist. The constant also appears in the relation between a particle's momentum and its wavelength, expressed as lambda equals h/p. This idea, introduced by Louis de Broglie, showed that matter has wave-like aspects. The wavelength of a particle depends inversely on its momentum, and the scale of this wave behavior is set by h. For everyday objects, the wavelength is unimaginably small, but for electrons, it is large enough to produce interference and diffraction. Again, Planck's constant determines when classical particle pictures fail. Perhaps the most famous appearance of h is in the uncertainty principle formulated by Werner Heisenberg. The product of uncertainties in position and momentum cannot be smaller than a quantity proportional to h. This is not a statement about experimental limitations, but a fundamental feature of nature. The constant thus encodes the limits of knowledge at the microscopic scale. It tells us that the classical dream of exact trajectories is impossible in the quantum realm. Planck's constant also governs the dynamics of quantum systems through Schrödinger's equation, where it appears as a factor controlling how wave functions evolve in time. The presence of H ensures that energy and frequency are linked, and that the evolution of quantum states involves oscillations at rates determined by energy differences divided by H. The constant acts like a bridge between the abstract mathematical description and measurable physical quantities. What makes H so remarkable is its universality. It does not belong only to radiation or atoms, but appears in phenomena ranging from superconductivity to the behavior of semiconductors, from the stability of white dwarf stars to the operation of lasers. Whenever quantum mechanics is relevant, Planck's constant is there, setting the scale of effects. It is as fundamental as the speed of light or the gravitational constant, defining a basic aspect of reality. Historically, the recognition of its significance grew gradually. Planck himself initially saw it as a parameter tied to his radiation formula. But as quantum theory developed, the constant took on deeper meaning. It became clear that H is not derived from other quantities. It is a fundamental constant of nature, measured experimentally and woven into the fabric of physical law. The smallness of H also carries philosophical weight. It suggests that the world of human experience is only an approximation, a large-scale limit where quantum discreteness blurs into apparent continuity. Our intuitions, shaped by macroscopic interactions, are not reliable guides to the microscopic domain. Planck's constant quantifies the distance between these realms. In practical terms, the constant has enabled technologies that define modern life. The understanding of electron behavior in solids, governed by quantum mechanics and H, underlies transistors, computers, and communication devices. Lasers, magnetic resonance imaging, and countless other tools depend on principles where Planck's constant plays a central role. A number once introduced to fix a theoretical curve now shapes the technological landscape. The meaning of Planck's constant is therefore multifaceted. It represents the size of energy quanta, the scale of action, the link between waves and particles, and the limit of precision in measurement. It marks the threshold where classical descriptions fail and quantum laws take over. Its presence in equations is a signal that nature is operating at its most fundamental level. In the end, Planck's constant reminds us that reality has a grain, a smallest unit of action that cannot be subdivided. It tells us that energy, motion, and information are structured in ways that defy classical smoothness. From the glow of a heated cavity to the inner workings of atoms and the behavior of advanced materials, this tiny constant stands as a measure of the quantum world, quietly shaping the structure and behavior of everything we see. When Max Planck presented his radiation formula, he believed he had solved a specific technical problem. He had found a mathematical expression that matched the observed spectrum of thermal radiation, and he had introduced a new constant to make it work. To him, it was a cautious step, almost a reluctant compromise. Yet the idea hidden inside his derivation carried consequences far beyond his intentions. It marked the moment when physics crossed a boundary into an entirely new conceptual landscape. The key lay in the assumption that energy exchange between matter and radiation occurred in discrete amounts. Planck had treated the oscillators in the walls of the cavity as if they could only possess energies that were integer multiples of a basic unit proportional to frequency. He did not initially claim that this quantization was a fundamental property of nature. He hoped it might someday be explained by deeper classical mechanisms. But the success of his formula depended critically on this assumption. Without discrete energy elements, the curve of blackbody radiation could not be reproduced. This was the seed of quantum mechanics, though no one yet used that name. For centuries, physics had relied on the idea of continuity. Quantities changed smoothly, and differences could be made arbitrarily small. Planck's step introduced a grain into this smooth picture. Energy came in indivisible packets, and transitions between states occurred as jumps rather than gradual flows. Even if Planck saw this as a formal device, it hinted that nature at small scales might be built from units, not continua. The deeper significance of this shift became clear only when others began to explore its implications. In 1905, Albert Einstein took Planck's energy quantity seriously and applied the concept to light itself. To explain the photoelectric effect, he proposed that light behaves as if it consists of localized packets of energy, later called photons. This was a bold extension. Planck had quantized the interaction between matter and radiation. Einstein quantized the radiation field itself. Suddenly, the wave theory of light was no longer the whole story. Light had a particle-like aspect tied directly to Planck's constant. This development showed that Planck's idea was not confined to a special situation. It pointed toward a universal principle governing microscopic processes. The quantization of energy explained why electrons ejected from metals had energies depending on light frequency rather than intensity. Classical waves could not account for this behavior, but energy packets could. The notion that energy came in quanta began to unify previously puzzling phenomena. At the same time, the structure of atoms demanded attention. Spectral lines, sharp and discrete, suggested that atoms could emit or absorb only certain energies. Niels Bohr built on Planck's constant to propose that electrons in atoms occupy discrete energy levels. Transitions between these levels involved the emission or absorption of light quanta, with energies given by differences between levels. This model explained the spectrum of hydrogen with remarkable accuracy. Once again, quantization appeared as the key. As these ideas accumulated, it became impossible to treat Planck's assumption as a mere mathematical trick. The constant he introduced had become a cornerstone in multiple areas: radiation, atomic structure, and the interaction of light and matter. The emerging framework required a new language. Classical mechanics, based on precise trajectories and continuous variables, could not handle systems where energy levels were discrete and transitions probabilistic. The birth of quantum mechanics was therefore not a single event, but a gradual realization that the classical world was insufficient. Planck's work was the first decisive break, even if he did not recognize its full meaning. His constant served as a marker of the new domain. Wherever H appeared, classical reasoning failed and new rules applied. The conceptual transformation was profound. In the classical picture, a system's future was determined exactly by its present state. In the quantum picture that developed, only probabilities could be predicted. Energy levels were discrete, and measurements influenced outcomes. The smooth curves of classical trajectories were replaced by wave functions and probability amplitudes. These ideas would take decades to mature, but their origin can be traced back to Planck's hesitant step. Another aspect of this birth was methodological. Planck's solution showed that empirical data could force a change in foundational assumptions. The authority of classical theory yielded to the demands of experiment. This set a pattern for 20th-century physics, where bold theoretical proposals were guided and constrained by precise measurements. The quantum revolution was rooted in observation, not speculation alone. The new mechanics that eventually emerged incorporated Planck's constant at its core. It appeared in the commutation relations of operators, in the equations governing wave functions, and in principles limiting measurement precision. The constant defined the scale at which quantum effects became significant. Systems with actions much larger than h behaved classically. Those comparable to h required quantum treatment. This boundary clarified why classical physics had worked so well in the macroscopic world, despite being fundamentally incomplete. Looking back, the irony is striking. Planck aimed to preserve order, yet his work initiated a revolution that overturned deeply held intuitions. The birth of quantum mechanics began not with dramatic declarations, but with a careful fit to a radiation curve. From that modest origin grew a theory that redefined matter, light, and information. The legacy of this moment extends far beyond academic theory. Quantum mechanics, built on Planck's constant, underlies modern electronics, chemistry, and materials science. The behavior of semiconductors, lasers, and superconductors all trace back to the quantization principle, first introduced in the Blackbody problem. What began as an abstract constant in an equation now shapes the technological world. The birth of quantum mechanics thus illustrates how a small conceptual change can have vast consequences. By allowing energy to be discrete, Planck opened the door to a new understanding of nature. The constant h became the symbol of this shift, marking the departure from classical continuity to quantum discreteness. From this point forward, physics would explore a reality that is not smooth and predictable in the old sense, but structured, probabilistic, and profoundly surprising. When the idea of energy quanta first appeared, it was tied to the exchange of energy between matter and radiation. The concept was cautious, almost reluctant. Yet a few years later, Albert Einstein took a step that expanded the scope of quantization far beyond its original setting. He suggested that light itself, long understood as a wave, could behave as if it were made of discrete packets of energy. This move transformed Planck's constant from a technical parameter into a universal feature of nature. Einstein's reasoning grew out of a puzzling experimental phenomenon known as the photoelectric effect. When light shines on certain metals, electrons are ejected from the surface. Classical wave theory predicted that increasing the intensity of light should increase the energy of emitted electrons, since a stronger wave carries more energy. But experiments showed something different. The energy of the ejected electrons depended on the frequency of the light, not its intensity. Below a certain frequency, no electrons were emitted at all, no matter how bright the light was. Above that threshold, electrons appeared almost instantly, even at low intensities. This behavior made sense if light energy came in packets, each with energy proportional to frequency, as Planck's relation suggested. An electron could absorb a single packet and be freed from the metal if the packet's energy exceeded the binding energy. If the frequency was too low, no packet had enough energy, regardless of how many arrived. Intensity then determined how many electrons were emitted, not their individual energies. Einstein's interpretation treated light quanta, later called photons, as real entities. It was a bold proposal, challenging the deeply established wave picture of light. Planck's constant stood at the center of this idea. The energy of each photon was given by E equals h nu. The same constant that had appeared in Blackbody radiation now governed the interaction of light with matter. This connection hinted at a unifying principle. Quantization was not limited to a special case, but was woven into the nature of electromagnetic radiation itself. Einstein's work did not stop there. He explored how quantization might affect the motion of atoms and molecules, contributing to the theory of Brownian motion and strengthening the case for the atomic theory of matter. But it was his light quantum hypothesis that truly extended Planck's idea. It showed that quantization could explain phenomena that classical theory could not, giving the constant h a broader role. The expansion of quantum theory continued with the study of atomic spectra. Niels Bohr, inspired by both Planck and Einstein, proposed that electrons in atoms occupy discrete orbits with specific energies. Transitions between these orbits involved the emission or absorption of photons with energies determined by differences between levels. Planck's constant entered again, linking the frequency of emitted light to the energy change. The sharp spectral lines of hydrogen, long a mystery, fell into place within this framework. As these developments unfolded, the notion of quantization spread to other areas. The specific heat of solids at low temperatures, which classical theory had failed to explain, could be understood by treating vibrations of atoms in a crystal lattice as quantized modes. Each vibrational mode, like Planck's oscillators, could only carry energy in discrete units. This idea, developed by Einstein and later refined by Debye, showed that quantization was relevant to the thermal properties of matter. Louis de Broglie took the next conceptual leap by proposing that matter itself has wave-like properties. If light, a wave, could behave like particles, perhaps particles could behave like waves. He introduced the relation between momentum and wavelength involving Planck's constant. Electrons, once thought of as tiny billiard balls, now possessed wavelengths that could lead to interference and diffraction. Experiments soon confirmed this wave nature of matter, further entrenching h as a universal constant. The expansion of quantum theory thus transformed the constant from a parameter in a radiation formula into a bridge connecting waves and particles, matter and light. Planck's constant became the scale at which classical distinctions blurred. Objects were no longer purely particles or waves. They exhibited aspects of both, with h governing the transition. This broader framework required new mathematical tools. Werner Heisenberg developed matrix mechanics, and Erwin Schrödinger formulated wave mechanics. In both approaches, Planck's constant played a central role. It appeared in commutation relations and differential equations that described how quantum systems evolve. The constant determined the size of quantum effects and the spacing of energy levels. Without it, the new mechanics would collapse back into classical forms. The uncertainty principle provided another perspective on the importance of h. It established a fundamental limit to how precisely certain pairs of quantities, like position and momentum, could be known simultaneously. This limit was proportional to Planck's constant. The principle was not about measurement imperfections, but about the structure of reality. The constant thus encoded a fundamental feature of nature's indeterminacy. Einstein's initial extension of quantization to light had opened the door to all these developments. What began as a solution to a radiation problem had become a universal principle. The constant h linked diverse phenomena: the emission of electrons from metals, the spectra of atoms, the heat capacity of solids, the wave behavior of particles, and the limits of measurement. The intellectual journey from Planck to Einstein and beyond illustrates how scientific ideas grow. A concept introduced cautiously in one context can reveal deeper significance when applied elsewhere. Planck's constant became the thread connecting these advances, guiding physicists toward a coherent quantum theory. The expansion of quantum theory also reshaped philosophical views. The classical picture of a deterministic, continuous world gave way to one where probabilities, discrete states and fundamental limits replaced certainty. Planck's constant symbolized this shift. It marked the scale at which the old intuitions failed and the new principles ruled. By the time quantum mechanics was fully developed, the constant had become as fundamental as the speed of light. It appeared in the equations governing everything from atoms to electromagnetic fields. The early reluctance to accept quantization had faded, replaced by recognition that this tiny constant defined the structure of the microscopic world. Einstein's role in this story highlights the power of taking an idea seriously. Where Planck had seen a formal assumption, Einstein saw a physical principle. His willingness to extend the concept of quanta to light itself accelerated the transformation of physics. The expansion of quantum theory thus built on Planck's foundation, spreading the influence of H across the entire landscape of modern science. By the time Planck's constant had woven itself into the equations of radiation, atomic structure, and the behavior of matter, it had become clear that this tiny number was more than a technical parameter. It marked a boundary in our understanding of reality itself. Classical physics had portrayed the world as continuous, deterministic, and ultimately predictable. Planck's constant quietly undermined that picture, revealing that at the most fundamental level, nature follows rules that challenge ordinary intuition. One of the deepest changes concerned continuity. In the classical world, energy, position, and motion could vary smoothly. Any change could be divided into smaller and smaller steps without limit. But Planck's constant introduced a smallest scale of action, a basic unit below which the classical description loses meaning. Energy exchanges occur in quanta, and systems can occupy only certain discrete states. This discreteness is not a matter of measurement limits. It is a property of nature. Reality, at its core, is not an unbroken flow, but a structured pattern of allowed possibilities. This shift also altered the idea of determinism. Classical mechanics suggested that if the positions and velocities of all particles were known at one moment, the future could be predicted exactly. Quantum mechanics, built around Planck's constant, replaced precise trajectories with wave functions that describe probabilities. The constant appears in the mathematical relations that limit simultaneous knowledge of certain pairs of quantities. The uncertainty principle, proportional to h, states that exact knowledge of both position and momentum is impossible. This is not due to experimental imperfections, but to the structure of the physical world. The future is no longer fixed in detail. It unfolds within a range of probabilities. Another transformation concerns the relationship between waves and particles. Before the quantum era, these were distinct categories. Light was a wave, matter consisted of particles. Planck's constant helped dissolve this separation. The relation between momentum and wavelength, involving h, showed that particles have wave-like aspects. Conversely, Einstein's work demonstrated that light, a wave, behaves in particle-like ways. Reality at small scales does not fit neatly into classical categories. Instead, it exhibits a dual character, with Planck's constant setting the scale of this duality. The structure of atoms provides a vivid example of how H reshapes understanding. Classical electrodynamics predicted that electrons orbiting a nucleus would radiate energy continuously and collapse inward. But atoms are stable, and electrons occupy discrete energy levels. These levels arise naturally when wave-like behavior, constrained by Planck's constant, is taken into account. The constant ensures that only certain standing wave patterns are allowed. Stability, chemistry, and the diversity of matter depend on this quantization. The world of substances colors, and biological molecules exists because of rules set by h. Planck's constant also redefines the concept of measurement. In classical physics, measurement could, in principle, be made arbitrarily precise. In the quantum domain, the act of measurement interacts with the system in ways governed by h. Observables correspond to operators whose mathematical properties involve this constant. Outcomes are not predetermined values waiting to be revealed, but are drawn from probability distributions. The role of the observer becomes part of the physical description, not an external spectator. Time and energy, linked through Planck's constant, gain a new relationship. Short-lived states can have uncertain energies, while well-defined energies correspond to long lifetimes. This interplay shapes processes such as radioactive decay and transitions between atomic levels. The constant thus connects the flow of time with the structure of energy in a way that has no classical counterpart. On a larger scale, Planck's constant influences the behavior of matter under extreme conditions. The pressure that supports white dwarf stars against gravitational collapse arises from quantum principles involving h. Even the properties of materials, from the conductivity of metals to the behavior of superconductors, depend on quantum rules. Though the constant is tiny, its consequences extend across the universe. Philosophically, the presence of a fundamental constant governing the limits of knowledge challenges traditional views about reality. It suggests that nature is not a fully transparent machine, but has intrinsic constraints. Some questions cannot be answered with unlimited precision because the answers themselves are not defined beyond certain limits. Planck's constant embodies this subtlety, marking the edge of what can be known. At the same time, h provides a unifying thread. It appears in equations describing phenomena as diverse as atomic spectra, chemical bonding, semiconductor physics, and the behavior of light. Its universality indicates that the quantum description is not a special case, but the foundation upon which classical behavior emerges as an approximation. The familiar world is a large-scale limit where the effects of h become negligible, smoothing out the discreteness and uncertainty that dominate at small scales. The change in world, brought by Planck's constant, is comparable to earlier scientific revolutions. Just as the realization that Earth orbits the Sun altered humanity's cosmic perspective, the discovery that action is quantized reshaped our understanding of matter and motion. It forced scientists to develop new mathematics, new concepts, and new interpretations of physical law. Yet this revolution did not eliminate the old theories. It placed them in context. Classical mechanics and electromagnetism remain valid where actions are large compared with h. They are approximations emerging from deeper quantum rules. Planck's constant thus acts as a scale factor, distinguishing regimes of applicability. Ultimately, the importance of Planck's constant lies in what it reveals about the fabric of reality. It tells us that the universe at its most fundamental level is not continuous but built from discrete processes. It shows that certainty gives way to probability, and that observation is intertwined with physical law. From the glow of heated matter to the stability of atoms and the behavior of stars, this tiny constant shapes the cosmos. The change it brought was not merely technical but conceptual. It replaced the image of a predictable clockwork universe with one of structured possibilities, governed by precise yet non-classical rules. Planck's constant stands as a symbol of this transformation, a reminder that even the smallest number can redefine how we see the world.